When you have nested trig functions or a function within its inverse, or the flipped version of it, so you have the inverse inside the function, they can be easy to work with as long as the angles are in the right interval. So we know sine and arcsine, well, arcsine specifically, is between the angles negative pi over 2 and pi over 2. Pi over 3 is within that. So that means that we can really just get rid of those things. They cancel each other. And our answer is just pi over 3. Tangent, our arc tangent is within the angle negative pi over 2 to pi over 2, just like sine. And pi over 4 is within that angle. So these actually just ends up canceling and gives us pi over 4. Cosine is between the, well, cosine inverse allows you to take any values between -1 to 1. 0 is in that, so that means that when you do both of this is going to give you cosine of pi over 2, or it'll just give you pi over 2. And then cosine of pi over 2 is 0. Of course, a similar thing can be done here. Once again, you're looking for numbers to be plugged into arcsine, or the inverse sine is between -1 and 1. Negative 0.5 fits within that, so it's fine. If you were to plug that into there, you're going to get negative 30 degrees, or pi over 6. And then sine of that will give you negative 0.5 back. So you can see we always get back what we started with because these angles were in the correct interval. Now let's consider quickly this case here. We have the square root of -1 squared. So think of it like, we have the function x squared and quote unquote its inverse, the square root. So what I've done here is I've done what I just did up here. I've nested the two together. So I have the square root of x squared. And in this case, it should just cancel out nicely, but it doesn't because these are not proper inverses. If I plug in -1 for x, if I evaluate this, I get -1 squared is 1, and the square root of 1 is 1, not -1. And once again, that's because these are not inverses or perfect inverses. If we did get -1, then they would be perfect inverses, but again, they're not. So a similar thing happens when you look at these angles that are outside of the range. So first off, we have pi here, and that's outside the scope of arcsine. But what happens is it's going to be ended up being shifted. So sine of pi is going to be, let's see, pi is 180 degrees. Sine of that is going to be 0. So we have sine inverse of 0. Type into your calculator, you're going to see sine inverse of 0. That's going to give you an angle of 0 degrees, or 0 radians. It does not give us back pi, it gives us back 0. Okay, cosine of 7 pi over 6. 7 pi over 6, this is 6 pi over 6, 7 pi over 6 is going to be 30 degrees past that. So just like here, this is 7 pi over 6. And the cosine of that is going to be, well, this is going to be longer, and the x is going to be root 3 over 2. So we're going to have our cosine of root 3 over 2. And our cosine of root 3 over 2, going backwards, you can plug into a calculator if you want. That's going to end up giving you 30 degrees, or pi over 6. Once again, not back to the 7 pi over 6 like we would kind of want, but it doesn't happen that way. Okay, tangent of -17 pi over 4. This is going to be the arctangent of, that's going to be -1. Tangent inverse of -1 is going to give us back negative pi over 4. Or the same thing as negative 45 degrees. So you're always going to be, if you have this this inverse function last, you're always going to be restricted back to the range that the inverse has. So for sine, it'd be negative pi over 2 to pi over 2. The same thing with tangent, or arctangent. For our cosine, you're going to be within the 0 to pi, that range of angles. Now, in all the above examples, we looked at a trig function and its own inverse. But we could have different trig functions together. As you can see here, we have cosine and arctangent. So to solve this thing, really what we want to do is create what's called a reference triangle. We've already seen this before. But a reference triangle, and specifically to this case, where we're looking at two different trig functions, and we're going to use right triangle trig to solve it. So we have cosine and arctangent. Now, arctangent, right, this is just an angle. So you could say that this tells us that tangent of theta equals 12 over 5. And from that, we can create a right triangle. Now, 12 over 5, tangent is y over x, so we can think of this as y over x like this. And doing the right triangle trig, we're going to get 12 squared plus 5 squared equals c squared. This is, of course, c. That's going to give us 169, and that tells us that c is 13. Okay, to make a right triangle within the unit circle, we can, of course, just divide everything by 13. And that'll give us a radius of 1. So now we can find cosine of this angle quite easily, is just the x-coordinate. In this case, the x-coordinate is 5 over 13. And we know that it's going to be positive because arctangent only will ever give us an angle between the angles of negative pi over 2 and pi over 2. Now, because it's a positive value inside the tangent, we're going to get positive values on the outside. If we had a negative value on the inside, so negative 12 over 5, that would tell us that we're in this negative range here. And so we would actually have not in this quadrant, but actually it'd be in the fourth quadrant. So it's important to always think in mind, or keep in mind what the graph looks like of the inverse functions, and when do you expect positive or negative angles, or angles that are in the first or second quadrant for our cosine. But this is what we get for this whole scenario, 5 over 13. Okay, now we're going to do the similar kind of thing, but now we're going to look at what if we have variables in it. Still, it's going to be the same process. Cosine inverse of 1 minus x. So we know that cosine of theta equals 1 minus x. It's just equal to an angle. So we can move that around. Cosine is adjacent over hypotenuse. So when we look at the reference angle, we have the adjacent over the hypotenuse, but of course the hypotenuse is just 1. There's nothing in there, so it's just going to be 1 there. And to find sine, we need to know what the opposite side of the angle is. We don't have that, we can use right triangle trig. So the opposite side is going to be the hypotenuse minus the adjacent side squared equals the opposite squared. And we can simplify this down a little bit, just expanding everything. So we have 1 minus 2x plus x squared in parentheses. And then simplifying a little bit further, that's going to give us 1 minus 1 plus 2x minus x squared equals, so the opposite's going to be the square root of 2x minus x squared. And that means that sine of theta, which is exactly what this is, right? We said cosine of theta equals that. That's the same thing as saying theta equals cosine inverse of 1 minus x. And that is the same thing as just right there. So cosine of theta, which is exactly what we're trying to find, is just the opposite over the hypotenuse, which is just the square root of 2x minus x squared. So these reference triangles really help you solve these kind of problems that have, different nested trig functions, especially when you have inverses in there. But they can also help you with a lot of different kinds of scenarios. So give it a try. Number 2.